Hello, welcome to the third epistemic inquiry workshop. We are going to apply this methodology that has been the focus of the first two workshops to the unit that you're now working on about chemical reactions. I'm just going to give a quick overview of what we've done so far. We looked at what epistemic inquiry actually is, how it is taught, and how it relates to the three worlds of Karl Popper, and then how it can be applied to units. Previously, we looked at other units. Now we're looking at how it can apply to chemical reactions. Remember, epistemic inquiry is about these big questions: what exists, how do things happen, how do we come to know, and what we can do with this knowledge. These are very, very appropriate in this chemistry section in terms of that we have observable phenomena, but we also are starting to push students towards the models of atoms and particles in terms of explaining how things happen and how we come to know. These are going to be major parts of any kind of chemistry education. Also, obviously, we'll be looking at how chemical reactions and chemical knowledge can be applied. Remember the 5 principles coming from cognitive acceleration methodology. We will do a lot of concrete preparation in terms of demonstrations of chemical phenomena, looking at the features of models to try to explain them. We'll ask students again to do a lot of predicting and explaining, often in small groups, developing their ideas, which often we will then lead to observations that either confirm or deny their explanations and predictions. Social construction will be very important, where the teacher is leading the dialogue in the class to try to look at how explanations and predictions can be brought into line with the results that are being demonstrated and talked about. There'll be a big focus again on how we get to know and how we monitor how our thinking is developed. And then this metacognition and bridging will be applied beyond the simple phenomena we look at to a broader set of phenomena. Okay, remember the 3 worlds of Karl Popper. The physical objects will be the liquids, solids, and gases that are produced as products of chemical reactions, or the physical objects that are the reactants involved. There will be a lot of subjective experience when observing chemical reactions, and also explanations that they may have developed from their previous experience. And we'll be using a lot of language, in particular the language of modeling, of how we explain what's going on beneath the surface of these observations. So the 2 chemical reactions we're going to be looking at are 2 liquid reactants, sodium thiosulfate and hydrochloric acid. And we'll be looking at the effect of concentration in particular. And then a slightly different, but with magnesium, a solid reactant, reacting with a liquid reactant. And in this case, producing one of the products will be a gaseous product. Through this, we'll be doing lots of demonstrations. There are opportunities for the teacher to guide the social construction of understanding, to elicit student ideas, to elicit their predictions and explanations, and also to be able to demonstrate observations that either confirm or conflict with their predictions and explanations. Also, we'll be introducing a very simple collision simulation model of how particles need to interact to move from reactants towards products. And as in previous workshops, we'll be using a lot of the idea of predicting and explaining and observing and re-explaining. So now moving on to 2 short videos that actually show what these 2 reactions are.
Today we're going to do an experiment, and we are going to work with hydrochloric acid and sodium thiosulfate. And the way this experiment goes is that when you combine the 2 together, you actually make a precipitation reaction. You're going to make solid sulfur. And we often use this as a way of examining the influences of temperature, concentration, or agitation. We basically can see whether the reaction is happening faster or slower with those factors by being able to see how quickly the solution goes cloudy, particularly how long until you can no longer see through it. So how we achieve this is that we often have like a marking. So here I've got a piece of card with a bit of blue tack. So I could sticky tape it, I could stick it to behind the test tube here. Often this one's done when you view from above. And as it starts to get cloudy, and you have your X mark underneath, you would view from above and you just basically time how long until you can no longer see the mark. For us, because of the camera, I can't seem to get it from above like the traditional method. We've just modified this experiment slightly by putting it side on. So I'm going to try and stick it there. And I'll get you a close-up in a moment. But the theory goes is that you'll get a precipitate, it'll start to build up and build up and build up until we can no longer see through it, and we'll take a time measurement. We are going to try and see the influence of increasing the concentration of sodium thiosulfate and see how that makes this thing go quicker or slower. Okay, so we're just going to have a quick demonstration of what the reaction looks like before we proceed to use the little X mark there. So I'm just going to add the two reagents together. We've currently got the hydrochloric acid in there, and now I'm going to add a dilute sample of sodium thiosulfate, and we should start to see a reaction starting. Okay, so now the solution has gone quite opaque, and we might just finish this one here for the moment being, but you can start to see that we do build up that amount of sulfur as a colloid. So now we're going to run this experiment a few times at different concentrations, and we'll use a stopwatch. I'm not sure if I'll have it visible on the screen. I might just have it off camera just to keep things nice and simple. But maybe I'll put these side by side so you can see them all playing out side by side on the video all at once, and then we can look at some graphs later on.
In this reaction, we're going to look at the reaction between magnesium and hydrochloric acid. And you can see this is magnesium tape. It's like a metal ribbon, and I've just cut it up into little pieces, but you can see here it's kind of silvery, it's kind of gray. It's soft and bendy, you can bend it no problem. And I'm going to add one of these little pieces into my test tube of hydrochloric acid. So there I've got one piece. Here's my hydrochloric acid. Let's see what happens when we drop that in there. Look at that, bubbles forming. It's dancing around on the surface there. You can hear it. Oh, you might even be able to see that little bit of smoke. Yep, there's a little puff of smoke. If I put it on the black background, you can see that. Little puffs of smoke happening there, so you know this reaction is hot. It's an exothermic reaction. It's producing heat, and it's bubbling away there like crazy. Now what if we wanted to test what gas is being produced? We've got magnesium and hydrochloric acid. What do you think those bubbles of gas are? How could we check? Well, we've done this before. One way we can check is by using a burning splint. So I've got my splint here. I'm going to light it on fire. And we're going to see what happens when we put it into, I'm going to make a fresh batch of our magnesium in our hydrochloric acid, and then we'll see what happens. I'm going to tilt my camera up a little bit so you can see the top here. Okay, so I'm going to take one of these pieces of magnesium ribbon. I'm going to drop it in there. It's bubbling away. Give it a few seconds to make some of that gas. And let's listen carefully. What's going to happen if I put my burning splint in there? Oh, scared me. Did you hear that? Let's see if I can get it going again.
So, I would introduce this model in a very simple way to begin with, of just setting it up with the default settings, which is 20 of reactants A and 20 of reactants B, and say that scientists talk about particles of matter colliding, and that often is when chemical reactions happen. And so I'm just going to start it and run it for 20 seconds. And the scaffold for the students is, what do you notice and what do you think is happening? Okay, then I would start using the model to explain some of the variables that are important. And the variable that I think from the first two demonstrations, and the one that we want to focus on first, is the idea of concentration. And I'm going to set this up where I'm going to say there's a large vessel here that's represented by the square, just like the contents of the test tubes in the demonstrations. And there are a number of particles. Now, so what I'm going to do now is increase the number of a reactant and set it up. And I'm going to ask the students, what do you now notice? And this is where you can introduce the idea of, in the same space, or the same volume, same space in this model, volume in the actual physical objects, the solutions, the test tubes, there are more particles of A than B. And I'm going to ask them, well, can you predict and explain what you think will now happen? And again, we're going to run it for 20 seconds. And I would field all of the ideas and discuss them, and just maybe record them on the board, or get the students to record them on mini whiteboards before we run the simulation. So here we've doubled the concentration of one of the reactants. Later, we'll be able to do that with the sodium thiosulfate and the hydrochloric acid, and come back to this result when we see actually how long it takes for the opacity to make the cross invisible. And this result will be able to record. You can record this on a table, or you could have given the students a table knowing what kind of simulation parameters you're going to use. And then, of course, it might be reasonable to say, well, what's going to happen if we double the concentration of the other reactant? But actually, I would stop using the simulation and go back to a physical experiment and work your way through variables, each time hearing the predictions and the explanations, and then the response to the observations, and come to the simulation to show that a model is useful for us to try to work out what is actually happening. And so we would move between these three strategies: observations being used to create cognitive conflict, asking students then from the growing set of observations to make their predictions. I would mediate their thinking to say, let's have a look at the results you've got so far. Can you bring them into your explanations? And so we would work our way through systematically. I think a very easy strategy without too much ratio thinking is the idea of one reactant doubling or halving the concentration, while the other one stays the same. And then the move of, okay, what if we do that in reverse, where the other one stays the same, and the one that we didn't change, we double and halve. And then moving on to where you combine, where you have doubling of both or halving of both. And this is a whole set of experiments that you can demonstrate, go back to the model and demonstrate, before the students move on to do some hands-on experimentation of their own. Thank you.